Right, let's look at scaling and coding. Suppose we have a data set, and this data set X is modified to give us some new sets. Let's call them Y and Z. Okay, and the mean and standard deviation of the data set X. So here's X over here, and it's 1, 2, 3, 4, 5. The mean is 3, and the standard deviation is 1.58. If we take our X values and add 2 to them, we generate a new set Y. And this Y has a mean of 5 and a standard deviation of 1.58. As you can see, the standard deviation hasn't changed, but the mean has. So when we've added a number, naturally when you add them all up divided by the number of items, the mean changes. However, if you just add a number, the deviations from that mean stay the same. Say now we take X and we multiply it by 10 to generate this new data set Z. Okay, so instead of 1 we now have 10, 20, 30, 40, 50. This now has a mean of 30, so the mean changes, and the standard deviation also changes to 15.18. So it seems like, from what we've seen so far, it seems like the mean and standard deviation change if you multiply it by a number. However, if you're just adding a number, the standard deviation remains the same. It's only the mean that changes. So what would happen if we combined it? So we added and multiplied a data set by a number to generate a new set. What would the mean and standard deviation look like? Right, we've got an example here. Here's our data set X again. So you've got 1 to 5 with the mean of 3, standard deviation 1.58. This time we're going to take X and we'll times it by 10 and then add 2 to generate a new data sample. And this will give us 12, 22, etc. all the way to 52. So this time the means changed to 32 and the standard deviation is 15.8. Can you see a pattern? So that means if we take the standard deviation is unaffected by the 2. So if you take the 1.58 and times it by 10, it gives you the new standard deviation. And the mean 3, if you times it by 10, you get 30, add the 2, gives us 32. Let's see if we can summarize this data using some equations. So with linear coding, if we've got a variable, if we've got a data set X, and we times it by, say, B, and we add a number to it, A, and it gives you a new data set, let's call that Y. Okay, then this has a mean of X bar and a standard deviation which we'll call SX. I'll write down standard deviation of our X values. So it turns out that the mean, okay, if we take the mean, so with the X bar value, with the X values, the mean is also changed by multiplying by B, adding A, and it gives us our new mean. Okay, so Y bar is our new mean. However, for the standard deviation, if we were to take the standard deviation, we would simply multiply it by B. It's not affected by A, and that will give us our new standard deviation for Y values. So SY equals our standard deviation for the Y values. So that's a relationship between the mean and the standard deviation between two sets of data that have been transformed by a linear relationship. Let's look at a few examples for how this would work. So say we have a data with mean of 8 and a standard deviation of 3, and it's coded using y equals 4x minus 5. Okay, the question is find the new mean and standard deviation. Right, so for the mean it will be x bar times 4 take away 5, and for the standard deviation it will simply be 4 times the standard deviation. And so therefore if we substitute the numbers in, we get the new mean to be 27 and the standard deviation to be 12. As another example, a set of exam results have a mean of 36 and a standard deviation of 8. They are coded, so the mean is 50 and the standard deviation is 10. We need to find the formula for the coding and see what an original mark of 72 becomes. Well, firstly, let's put our information together. We know it's a linear code, and so we've got y equals ax plus b, and the original mean is 36 and the standard deviation is 8. So and they're to be coded, and when you code them, so if we code the mean, we move from our 36 to 50. So here we've got the 36 and here we've got 50, and obviously the mean is affected by A and B. With the standard deviation, however, we go from 8 to 10, and it's unaffected by the number that's added on. It's simply multiplied by A. So you take A times it by A, and 8 times A, and that gives us 10. That gives us a set of two simultaneous equations. Over here, in fact, they've got a nice little summary of how the mean x bar changes to the new mean y bar, and the standard deviation of x is transformed to a standard deviation of sample y. Now we can solve this simultaneously, and it gives us a equals 1.25, b equals 5, and we can therefore write our formula. Now if the original mark is 72, we can simply substitute that into the formula, and out comes 95. Right, let's look at another example, and it's one where in an enterprise scheme every week Dora bakes 20 cakes in total. For each one she sells, she makes £1.20 profit, but she makes a loss of 40p on each cake that is not sold at the end of the week. Show that the total weekly profit is given by this formula. Right, so maybe we should set this up. Firstly, the profit in pence on each cake is 120x for x cakes are sold, and what's left over will surely would be 20 takeaway x is left over. And so if 40p is lost on each cake, then our loss is going to be 40 times by 20 takeaway x is our loss. So therefore our total profit is going to be the profit takeaway loss, which is 120 pence times x for each cake sold. Takeaway 40 times 20 takeaway x, which is obviously our loss, and that expands and simplifies to 160x takeaway 800. Right, in the next part we've been given the standard deviation and the mean. The mean is 17.7 and the standard deviation is 2.7, and what we want to do is find the mean and standard deviation of our weekly profits, given that it's coded. Now we know the mean will simply follow that linear equation, so we can take our mean times it by 160, take away 800, and that gives us 2032, and our standard deviation is simply multiplied by 160, and that gives us 432. Right, let's look at an example that involves some class width and a frequency distribution, and what we're going to do is use linear coding to work out the mean and standard deviation. So with an example like this, what we can do is firstly, to work, since it's a frequency distribution, we'll have a formula for our standard deviation and mean. For that we'll need some midpoints, so we'll take the midpoints between in the class interval here, and we generate these points x. Now the whole point of coding is to simplify large numbers. So one of the codes that we can use, and it's not in concrete, but it's not set in concrete, but it's something, as long as it works and it simplifies the numbers, giving us our aim should be really to get integer numbers, then it's fine. So y equals x take away 5 over 10, and we generate this new set over here. So we've coded our x into a new set y. We can then apply, we know what the frequency is for each interval, and we can work out the sum of fy, the sum of f, and the sum of fy squared. Once we've got that, we can then simply work out the mean. That would be 61 over 30, and the standard deviation, which is SYY divided by -1 square root, and that gives us, you might want to check this, it should give you 1.245. However, that is the mean and standard deviation for our data sample y. We want the mean and standard deviation for data sample x, so we'll therefore have to decode our results. So let's look at the coding that was used. It was x minus 5 over 100. We can rearrange that to form an equation of x in terms of y, and then simply substitute the mean into that linear equation. Okay, and that gives you 25.33, and the standard deviation is not affected by the number that's added, it's only the one that's multiplied, in which case it's 10. So we do 10 times the standard deviation of y gives us the standard deviation of data sample x, and that should be 12.45.